Good afternoon. I'm thankful to organizers of Cosmology 2023 in Miramare that give me a possibility to be this nice place again and present our current results on the predictions of global signal in the redshifted 21 centimeter line from dark ages in different cosmological models. Dark ages began after complete cosmological recombination of hydrogen and lasted up to redshift 13 when the ultraviolet radiation of sources started to ionize hydrogen again. This epoch is called as cosmic dawn. Which is ended by complete ionization of hydrogen at redshift about 6. The standard lambda CDM model predicts that temperature of cosmic microwave background radiation at the end of cosmic dark ages is about 80 kelvins. The temperature of gas is about 20 kelvins, and number density of hydrogen atom is about 1 per cubic meter only. It is a good time for increase of amplitude of density, initial density perturbation. Perturbations stop expansion in the peak of density perturbation, start collapse and formation of fast stars and galaxies. Because study of cosmic dark ages are important for understanding of physical conditions in which the first sources of light were formed. And I show here it is also interested for testing of some cosmology parameter and cosmological models. Important information channel from this epoch is a hyperfine structure line of hydrogen atom. During dark ages, hydrogen atoms are in ground state, which is hyperfine splitting with energy splitting about 6 micro electron volts that correspond 0.068 kelvins. When atom spontaneous transit from excited state with some spin 1 to 0, atom emit the photon with wavelength 21 centimeter or frequency 1420 megahertz. A lot astrophysicists and cosmologists discussed the possibility to detect this signal from a large redshift. This slide shows a scheme of formation and observation of signal from dark ages. Observer observe dark as observer hydrogen of dark ages is screened for a cosmic microwave background. So if a temperature of gas in dark ages is lower than cosmic microwave background radiation temperature, then we observe as absorption line. In opposite case, we will have emission line. The line is redshifted via the expansion of the universe in 1 plus z times. And simple dipole antenna on the S with fixed orientation, thankful to rotation of S from sometimes can observe all sky and detect sky averaged signal, which we call as global signal. Of course, this antenna must have also tuned for this frequency receiver, and we will have a signal from dark edges. Of course, it must be cleaned from background signal, foreground signal, and especially from ASLI radio interferometer signal. To compute signal from dark edges, we need to know the number density of hydrogen atoms, their temperature or temperature of gas, population of hyperfine structure levels, temperature of cosmic microwave background radiation. For that, we need to solve the system of differential equation, which include equation of kinetics for ionization and recombination, population, depopulation, and energy balance. Equation for kinetic of ionization and recombination of hydrogen and helium include photo and collision ionization from the ground state of atoms, photo recombination on all levels, and in non-standard cosmological models, such as model with self-annihilating dark matter, decaying, or other mechanism of ionization and heating can be. Equation for energy balance includes heating function for caused by Compton thermalization, Compton's photon cosmic microwave background scattering on free electron, adiabatic cooling as main heating cooling process, and also heating and cooling function in non-standard cosmological models. As a result of this the population kinetic equation, we obtain the dependence on temperatures on redshift for cosmic background radiation, red line, solid dark line for cosmic for baryonic gas, and a blue line show the spin temperature, which describes the population of hyperfine structure levels. This line is in the Relay Jeans region of thermal distribution of the distribution of thermal radiation. It is useful to use brightness temperature instead intensity. Transfer radiation equations give us exact expression for differential brightness temperature local from without cosmic background radiation, which we call differential, in such view. And it's for any Z. Computing differential brightness temperature for each Z in some range, we obtain a profile of line redshifted 21 centimeter line. It depends on cosmological parameters which is shown by this exact expression, and also implicit dependence on which is in a fraction of neutral hydrogen, and also spin temperature. At first, we study the dependence of value of depth and width, redshift 21 centimeter line on cosmological parameter in lambda CDM, standard lambda CDM model. For that, we variate parameters and compute for each set of cosmological parameters. But we need that equation for Friedman equation at current epoch, which is sum of omegas, baryon, dark matter, cosmological constant, and cavity was strongly 1. For that, we, when we variate, for example, density parameter for baryonic matter, we variate also omega lambda or omega k, from which line profile does not depend. We variate parameters around the fiducial lambda CDM model with parameters given by Planck collaboration 2020. One can see that increasing of omega b from green to down, the depth of line increases too. It is understand because absorber number of absorber increases too. Similar dependence is variation of density of dark matter parameter show also dependence, but very slowly. If for baryonic omega b baryon density parameter, 10% variation results in 17% of variation of depth of line. Then for dark matter omega, 10% variation of omega dm results in 4.3 variation of depth of line, essentially lower sensitivity. The dependence on Hubble parameter is larger. For example, 10% variation of Hubble constant around fiducial value give us about 28% variation of depth of line. Moreover, when we here is in this list of values of parameters Hubble constant, here is value given obtained on the cosmic microwave background data and also on the supernova 1A data. The difference between this value is about 30%. So when we will possibility to measure the depth of this line with enough accuracy, maybe we can help to solve the Hubble tension problem. In the next part of our work, we tested the non-standard cosmological model which has additional heating and cooling. In such model, the ionization and thermal history of baryonic gas is of course other, and we may expect that this line can give information about this. The first model which we tested was primordial stochastic magnetic, the model with primordial stochastic magnetic fields. Such fields can heating of baryonic gas caused by decaying magnetic turbulence and ambipolar diffusion. We test such model in the range of parameter lower than upper limit given by cosmic microwave background. For that we used the model of turbulence of primordial magnetic field given by Sethi and Subramanian 2005 and Hluba et al. 2015, which gives a heating function caused by decaying magnetic turbulence and ambipolar diffusion. It slightly changed ionization. Here is shown the dependence on of electron fraction on redshift for different values of amplitude of magnetic field, and a slight depends is caused mainly heating and dependence of photoelectron recombination on temperature. Here we show the dependence of baryonic gas on redshift by solid line for different model with different amplitude shown by color. In the left figure and in the right figure, we show the profile of a line for the same model. We show that for some value of amplitude of primordial magnetic fields, absorption line become emission line. Also, we tested the model with self-annihilating dark matter, product of which can be particle of standard model of particle physics. They can heat and ionize and excitate of atom and molecules. And again, we try the in the range of parameter which does not agree with current limits, observational limits for them. The temperature here is shown. We use a model of such dark matter model proposed by Hluba 2010. Here is shown the ionization history of the universe during dark ages after cosmological recombination during dark ages. Cosmic dawn and reionization here is not shown, and in next also because we do not take into account the ultraviolet radiation of first sources and effect Vossatian field effect. We see how history is changed, is increased fraction of electron with some generalized parameter of such model. The temperature also increases with energy deposited by self-annihilated dark matter in baryonic matter, and similar as in the previous model with primordial magnetic field, with increasing of deposited energy in baryonic component, the depth of line decreases and become at some values emission line. Similar situation is with non-standard cosmology with decaying dark matter, the product of which heat of baryonic gas ionize hydrogen and helium and excite atoms and molecules. And we again try such model in the range with parameter which do not disagree with other observational data, but the line is sensitive. We use Kluba and Liu and Steyer model for decaying dark matter. Here is ionization history. Here in the left figure, temperature history, and in the left one, decaying, profile of line. 20 redshifted 21 centimeter line. Upper scale shows frequency. So when we will have signal in this frequency range from dark ages, we can maybe obtain some values or upper limits on the parameters of this model. The general conclusions is that observations of 21 centimeter line redshifted from dark ages give us additional information about cosmological parameters of standard lambda CDM model, can resolve problem with Hubble tension, and give us information or upper limit on the parameter of non-standard cosmological models which can heat or cool baryonic matter. Thank you.